What's up, guys? My name is Emmanuel Williams, and this is my video on the tutorial on multiple expansion. So I discussed about the first problem where you were given a surface charge distribution on a disk. So this problem is where we are supposed to obtain the interaction energy between two dipoles, and to solve this problem, we know for a fact that the potential due to one dipole is given by this P1 dot r hat over 4 pi epsilon naught r square. So this is how the potential, you obtain this from the expression for the dipole contribution. So if we go backtrack a little bit, actually backtrack quite a lot, you'll notice that the dipole contribution is 1 over 4 pi epsilon naught r square, r hat dot r prime. So let's take out the r hat because it's independent of r prime. So when you do that, it's nothing but r hat dot this integral with respect to r prime, which is simply a constant. That is called the dipole moment. So that simply becomes this. So P1 r hat dot P1 dot r hat over 4 pi epsilon of r square. Now r hat over r square can be written as the negative of the gradient of 1 over r. Gradient of 1 over r is nothing but negative r hat over r square. And so this is nothing but P1 dot gradient of this. So this is how our system actually looks like. You have dipoles aligned arbitrarily, and the separation between them is given by the vector r. So for the convenience, for the sake of convenience, I'm going to shift my origin to the center of dipole P1. It's all the same if I work from a different origin, but it's just that we might have to deal with some cumbersome expressions. So for the sake of convenience, I'm simply going to shift my origin to the center of the dipole. Otherwise, the r vector will be r1 minus r2, where r1 and r2 are the centers of the respective dipole. It's r2 minus r1 actually, because we are taking this stuff at displacement. Right? So moving on, let's take the negative gradient of the potential. That's simply going to be the electric field. And that's 1 over 4 pi epsilon naught gradient of this quantity. We are taking the gradient of a dot product. And let's make use of the laws of vector calculus. Let's expand this using the identities that we've known. And you realize that there is a term where the del operator operates on P1. There's one term where you're using del cross P1, which zeroes out because P1 is a constant. And then you have an operator operating on P1, which again goes to 0 because that is 0, right? Because P1 is a constant. And then the reason why we wrote r hat over r square is pretty much evident now. So if you look at it this way, you would observe that you have a curl of gradient of 1 over r coming up. Now, is this curl always going to be 0? Now, the curl of a grad field is always 0. That is a property established in the vector calculus. But is it true always? Well, maybe not. It depends on how your grad field is defined and stuff. So, and we notice that the scalar field associated with that has a certain singularity at r equals 0. So maybe we are not in the clear. We might encounter some problems later on. And you'll see when we discuss about direct problems in a later video. So 3 terms drop out, become 0. You're left with one term, which when you do some careful analysis, this gives you the well-known expression of the electric field due to a dipole, which is 1 over 4 pi epsilon naught r cubed, 3 p1 dot r hat minus p1. This is a very famous expression for the electric field, and the potential due to the dipole. So the potential energy associated with a dipole whenever it is placed in an electric field is given by this minus P2 dot E. Now the electric field due to dipole 1, it acts on the other dipole, right? So there will always be some potential energy associated because of that. So let's put this E in the expression for U, and you essentially get back the same expression with which we started, right? Yeah. So we end up getting the same expression with which we started. So yeah, so this is about the second problem of the series. There's nothing much fancy about it. It's just a little bit of mathematical rigor, which is what you will find out when you do courses on electromagnetism. It's mostly mathematical rigor than there's a lot of mathematical rigor associated with electrodynamics in general, which is kind of good because it is applicable in other sectors in engineering, mathematics, and stuff. So this was the second problem, and I'll see you guys in the next video where we'll be dealing with a very interesting problem again. This one is going to be a very interesting problem because recall that the curl of a grad field is assumed to be zero in this case. But is it really the case? Because RR equals 0, you know that there is a singularity. So some problems might crop up as a result of this. And we are going to analyze this problem in this problem statement. So here we see that the complete expression for the electric field is given by this. We are going to get a rationale behind this and see how things work. So till the next time, take care everybody and stay tuned for the next video.